Well, we're continuing on frames and machines here in section 6.6. I just want to do a little bit of review with you, but if you remember in chapter 5, we did simple beams, simply supported beams that have a pin and a roller, like a pin and a roller, pin and roller, pin and roller, unless they were supported by a two-force member. And then we had two-force member problems where we had a strut or a string supporting two force members. And then remember that two force members don't have to be straight. They can be bent, and we still have the same line of action going through there. As long as the line of action goes through the two, as long as there's only pin connections at the end, then by definition the line of action goes through those pins, and so we still have a two force member. We also had tipping and balance problems where you could, if you were lifted too much load, you could tip over the front tire, or too much of a load on the crane, you might tip over here. We also had this problem we did in the lecture, in the video. Then we also had fixed support problems, where this was a special type of support compared to pins or tires or sawhorses. This one supports a moment. In other words, it requires a moment reaction for this to stay in equilibrium. As you push here, there has to be a moment going this way to keep it in equilibrium. Same thing here. There'd be moments in both of those cases. All right, so that's where we were with chapter 5. Also in chapter 5, we talked about constraints and whether there's too many support reactions and whether you could solve it. For example, if you just had a box, you're pushing on it and you had two pins here, then we understood that there are 4 reaction forces and it becomes statically indeterminate, meaning too many constraints. However, if we had something that looked like this, where instead of a box, it was just a strut problem, again, we have 2 pins. However, this is not statically indeterminate because we have a two-force member. And when the two-force member rules come into play, it allows us to do a little more advanced thinking. So then back to chapter 6, frames and machines. Again, we've just reviewing a little bit. We've talked about external forces and internal forces. These are external forces here. What goes on the inside is internal forces. When we had a truss, we only had 2 force members. Forces applied only and forces were applied only at the ends with pin joints or pin connectors. However, with frames, we have multi-force members, and forces and couple moments could be applied any place on the member. The ends may be pinned, or they may have fixed supports, or something else. So here's a frame. We haven't really looked at these quite yet, but it looks really simple. Is that we have a frame here with 2 pins. We've got a couple applied here and a single force here. The only way we can solve for reactions here is to what I call break it apart. And when you do that, you use the method of sections to isolate this part, and then method of sections to isolate that part. Where things meet together, these are called internal forces, and this is where the forces transfer equal opposite. So if I draw a free body diagram of this guy, I know that there's a pin reaction here. There's a couple applied. I don't know for sure what the directions of the forces are on BX or at B, so I'm just going to draw a BY this way and a BX that way. If I draw a free body diagram of this guy, it has a pin connection, a force applied. And where the forces are applied here at B, where they meet, these are called mating forces, and they have to transfer equal opposite. So in other words, if it goes that way on that member, it has to go that way on that one. If it goes that way on this one, it has to go that way on that member. So if we keep that equal opposite rule and equal opposite methodology with us all the time, most of the time we won't get too lost and the problems are. All right, so here's our process. In chapter 6, we're going to try to solve for external reactions that we can. Draw the entire free body diagram of the whole thing, look for all the reaction components, look for 2 force members as an opportunity to simplify. count the unknowns, and if there's more than 3 unknowns, that's an indication that you'll have to break it apart to solve, because we only have 3 equations of equilibrium. So then the process then is to break it after we find the external reactions that we can. Maybe we can't find them all. Then break it apart and find the internal forces that we're required to find. Separate the pieces, draw separate free body diagrams of each, write the equations of equilibrium for each piece, and just remember to transfer internal forces equal and opposite. Well, let's try to solve this simple frame problem here. What I've got is a frame with distributed force over here and 2 pins, and we are looking for the components of reaction at A and B. Okay, let's see what we got. Let's go ahead and look at our reaction forces first. I'll just say that there's an AY and an AX, and also a BY and a BX. Got that distributed force, and so I know that there's a resultant going this way, and the resultant is the distributed force of 2 times that 4, so that's equal to 8. Resultant is equal to 8 kilonewtons, and it acts at a distance here of 2 meters from that point. All right, let's try to find as many reactions as we can before we break it apart. So I'm going to sum the moments about B. What have I got? Sum the moments about B. I have AX goes through B, but I got negative AY times 3 plus the R times 2 is equal to 0. And I'm looking for AY here, plus 8 times 2 is equal to 0. So I have AY is equal to 5.33 kilonewtons. All right, so there's my first unknown. Can I find out anything else? I actually think I could sum the forces in the Y here and see what I get. Sum of the forces in the Y is equal to 0, so I got AY minus BY is equal to 0. So here's my second one. BY is equal to also 5.33 kilonewtons. All right, can I find out anything else for those reactions? And not yet. So let's go ahead and draw. Here, let's go ahead and break it apart and solve and draw 2 free body diagrams. So this one I'll draw over here. This will be the component here, the AC. I know there's an AY and an AX. And there will be a CY and a CX. This is 4 on that side and 3 on that side. Then over here I have this component, or this member. It's got 8 going in this direction, and oops, BY is going the other way, isn't it? So BY goes this way, and BX. And then here, where the forces transfer, or where the forces meet at point C, whatever direction I draw here, I have to draw them equal opposite over here in order for anything to work out right. So I draw a CX going this way and a CY going this way. Now, where should you start? Honestly, it doesn't matter, but because if I sum the moments about A, I'd have 2 unknowns here. I'm going to start over here and sum the moments about B. So let me scooch this up a little bit and see what we can come up with. All right, I'm going to sum the moments about B. And I have 8 times 2 minus CX times 4 is equal to 0. CY goes through B. So I can say CX is equal then to is equal to 4. All right, now that's not my reaction, but it is kind of key to my understanding. So I'm going to take that and I'm going to plug it in over here in this equation. Over here, on this free body diagram, over here, then if I sum the moments about A is equal to 0, I have Cx times 4 minus Cy times 3 is equal to 0. If Cx is equal to 4 and Cy times 3, I can solve that for Cy is equal to 5.33 kilonewtons. All right. And now that I have Cx and Cy and Ay, I should be able to sum the forces in the x to equal Cx. So sum of the forces in the x is equal to 0. So I got Ax minus Cx is equal to 0. So I got Ax is equal to 4.0 kilonewtons. All right, so how many reactions have I solved for? I've got Ax and Cx and Ay and Cy and By. I'm still looking for Bx. So now what I can do is go back over here, and sum of the forces in the x is equal to 0. I got Cx plus Bx is equal to 0. Oh, minus 8, beg your pardon. I got that 8 here. Minus 8 is equal to 0. So here I can solve for Bx is equal to 4.0 kilonewtons. All right, so now I've solved for all the pieces of the puzzle to get us going. Now, one thing we could have done here is recognized that this is a two-force member. I don't know if you did that when we were looking at this or not, but this happens to be a two-force member that is bent or crooked. What we do know is some rules about two-force members. We know that, I'm just going to put these in blue here, so I'm going to Cx is equal to Ax. That's a rule. Ay is equal to Cy. We also know that Ay is to the distance 4, and the same as Ax is to 3. So all of those ratios and things like that we did in Chapter 2, some of the other things that we've been doing since Chapter 2 can kind of help us go quickly when it comes to analyzing some of these more advanced kinds of